Hello everybody and welcome to a new video of the handout for the Fourier Transform class. In this case we have a new exercise. They tell us that we have a signal x of t for which we have the modulus and phase of its Fourier transform that we can see down here. So we can see that the modulus in the black pi function goes from 200 pi to 800 pi and half 1. And the phase of this Fourier transform is a linear phase crossing through 500 pi and with an angle of pi divided by 4. And outside of this 200 pi 800 pi window the signal value is 0. Okay, so the first question they make to us is to calculate the signal x of t corresponding to the inverse Fourier transform of x omega. So first of all, let's write here the analytical expression of x of omega. As said, it's a pi function with center in a certain omega 0 frequency and with a certain total width of 2w, capital W, and then the phase is a linear phase, which means that here the function is a linear function of omega, like this one. So the values of each of these parameters are omega 0, which is where the pi is center, is 500 pi, to the capital U, which is the total width of the pi, it's 600 pi, and the T0, which is the tangent of the angle, okay, it's tangent of before, which is 1. Okay, so that's the signal that they are giving to us, and we have to make the inverse Fourier transform of that signal. So in order to do that, we just realize that the signal has two distinct parts: the modulus part that we will call signal x1 of omega, and the phase part that we will call it x2 of omega. So that our signal x is the multiplication of x1 times x2. So if we made the inverse Fourier transform, the signal x of t that we are asked for will be the convolution of x1 with x2, and we have used the property that convolution in time translates into products in frequency. So let's go first and get x1 of t, which, as said, is the inverse Fourier transform of capital X1 of omega, which is the inverse Fourier transform of the pi function of omega minus omega 0 partido divided, by 2 capital U. So to do this inverse Fourier transform, we are using two facts. The first is that we have calculated in class, which is the inverse Fourier transform of the pi function W divided by 2 capital W in the past. We have done in class. Remember that the natural thing is to know which is the Fourier transform of the pi in time, which goes into a sinc in frequency, and the other way around, which is the inverse Fourier transform of a pi in frequency, will go can be calculated easily using the duality property. Okay, so using the duality property, we did this exercise. You know how to calculate this inverse Fourier transform. And then what we just observed is that we have the pi in omega minus omega 0, which means that we will also apply the shift in frequency property to calculate this Fourier transform. So do it in detail, and you should get the following expression: capital U divided by pi sinc of capital U divided by pi times time exponential of j omega 0 t. Okay, this exponential is coming from this displacement in frequency, and this sinc function is coming from the pi. Okay, let's go now for x2. x2 of t is the inverse Fourier transform of capital X2 of omega, which is the inverse Fourier transform of exponential j omega minus omega 0 t 0. Okay, and this is also very easy to compute, because this is basically a constant time the exponential, and basically the exponential is a shift in time. The k goes back as a delta, so you should get delta of t plus t0 exponential of minus j w0 t0. Okay, that's x2. Okay, we are almost there. Now that we have x1 and x2, x of t is the convolution of x1 and x2. So we have to convolve first the pi with exponential, so w divided by pi sinc w divided by pi time exponential of j omega 0 t. We have to convolve this with delta t plus t0 exponential of minus j omega 0 t0. In order to do that, we remember the delta property of convolution. So if we have a function ft and we convolve it with a delta that is displaced, for example, to the point t0, the result of this operation is just the value of the function, is displacing the function to the point where the delta was, so it's f of t minus t0. Do not get confused with the modulation property, which was multiplying and the result was a delta. This, in this case, is the convolution, the other big important property of delta. Okay, so if we apply this into this case, f of t will be this function here. Look, this is just a constant. So what we need to do is just change t in this expression with t minus t0, sorry, t plus t0, because in this case the delta is t plus t0. And the result is omega, capital omega divided by p, sinc omega t plus t0 divided by p exponential of j omega 0 t. Okay, this is x of t. And if we plug in the values that we have in the example or in the exercise, it will be 300 sinc of 300 times t plus 1 e exponential of j 500 pi t. Okay, just remember that because we will use it, that we have calculated that this is the Fourier transform, the inverse Fourier transform of the original signal that was pi omega minus omega 0 divided by 2w exponential of j omega minus omega 0 t. Just remember that, because you will use this result in the second part of the exercise. Okay, let's go to the second part. The second part, they are telling us that we should calculate a signal y, which is x of t plus 1 convolve with x of t plus 1. Okay, so let's go ahead and do this calculation. So first we realize that x of t plus 1 plus convolved with x of t plus 1 is exactly the following. Well, first, x of t plus 1, we can put it like x of t convolved with delta of t plus 1 by using the same property of the convolution with the delta, okay? Using this property. And then it's the same, convolved with it, with x of t convolved with delta of t plus 1. And then using the associativity property of the convolution, we can group these terms as follows. We can group x of t convolved with x of t, and then the convolution of delta t plus 1 convolved with delta t plus 1. Here you can see that we have a convolution of one delta, which we can consider a function, with a delta displaced. So we can apply this function, this property, and say that this is delta of t plus 2. So the result is that what they are asking us is the same as convolving x of t with itself, and then convolve the result with delta displaced 2 units to the left. Okay, so let's call this y sub 1 of t, and let's calculate it. Okay, we go into frequency, y1 of y, the convolution goes into the multiplication, will be x1 convolved with x1. Okay, so look, what we have is the convolution of x1 with of x no, sorry, I call x1, sorry, this is the convolution of x, sorry, I was making here a mistake, of x convolved with x. Okay, so x of x in frequency, we have it over here, is this expression here. This is x of omega. Okay, so we have to multiply, sorry, this is a multiplication, multiply x times x itself. So look, how do we multiply this with itself? So we multiply the modulus we have to multiply two frequencies, which are functions that are complex exponential. So it's a modulus part, which is the pi part, and then the phase part. So to multiply two of this, you just multiply the modulus and add the phases. This is how we multiply complex numbers. We multiply the modulus and add the phases. So we have to multiply the two pi's. So pi again times itself, it's itself. Okay, so pi times the same pi is the same pi. So this will be pi omega minus 500 pi divided by 600 pi. Okay, so this will be the modulus part. And the exponential, it's the exponential, which was aj omega minus omega 0 time omega 0 t. Omega minus omega. Here I made a mistake somewhere. Yes, the mistake is that this is t0. Sorry, this is t0. So this is t0, and I add two of those, so I put a 2 here. Okay, I already have y1. And then what I want to make is the inverse Fourier transform of y1 to get y1 in time. And I use exactly this relationship. I have a Fourier transform which is of this shape, as you can see. This is what I have over here, and I want the expression in time that I calculated in the first paragraph, in the first part of the problem. So using this, what we get is plugging the numbers. This is 300 sinc of 300 times t plus 2 exponential of j 500 pi t. Okay, we have y1 of t. But we are not done. We need to get y1. y1 is y1 of t convolved with delta on t plus 2. So the only thing we need to do is to displace this function y of t 2 units. So y1 of t will be 300 sinc of 300 of t plus 4, because I displace it 4 units, 2 units here plus 2 units due to the convolution with the delta, exponential of j, k, p, and t displaced 2 units. This is the result of the subject number 2. Well, let's go for the last part of the exercise. In the last part of the exercise, part C, they invent a new signal for which the frequency is given by a train of deltas. So a train of deltas that goes from k10 to k equal to 40, and the weight of the deltas is the value of the x of the first part of the exercise in frequency 20 pk, and the deltas are placed in omega minus 20 pk. Okay, and they ask me which is the period of this signal, which are the Fourier coefficients of its series development, and which is the average power of this signal set of omega. Okay, so in order to do that, we remember the relationship that there was between a signal, for example, set of t, that we had its Fourier series. So we had this summatory, sorry, this is a plus. So we know that the Fourier transform of this, we remember it was a set of omega, which was the summatory in k, and we just multiply by 2 pi the coefficient a sub k, and we transform the exponentials with deltas placed on k times omega 0. Okay, in our case, now we have what? We have, look, an expression that is already the deltas. So we have the summatory in k of 2 pi ak delta omega minus k omega 0. This is what we have. So this is what we have. This is what is given to us. Okay. This is part of the, well, this is given to us, okay? So, just identifying terms. So what we can get is then 2 pi ak is this value. 2 pi a sub k is equal to the value of the x function of the first part of the exercise in 20 pk. So here we just separate a sub k will be 1 divided by 2 pi, the value of the function x in the points 20 pk, and what is important is that the k's go between 10 and 40. Okay. So another thing we can get is that omega 0. Omega 0 is what multiplies the k. So what multiplies the k is 20p. So omega 0 is equal to 20p. And then T0, which is 2 pi divided by omega 0, will be 1 divided by 10. Okay, so we have this that they were asking for this. We have the AK coefficients. Okay, you just have to give numbers to the k figure over here, and you get the coefficients a sub k. They were asking us also the average power. So applying the theorem that we know how to calculate the average power from the Fourier series coefficients. This is the Parseval relationship. This is the average power. It's just adding together the modulus of the AK coefficients to the square, or a square. So in this case, the only coefficients that are not 0 are, or exist, are the ones between k, 10, and 40. And we have to take a modulus of a sub k squared. So we will need to take 1 over 2 pi, the modulus of x in 20 pk square. This is the thing that we need to do. So this will be, well, basically the square is over here, sorry. So we will have 1 divided by 2 pi square, and then we will have a summatory. For example, we will need first the modulus, the value of x on 2 pi times 10 square, plus, and go up, and the last term will be the modulus of x in 20 pi times 40 square. Okay, remember that the x function had a modulus that was always a constant, a constant 1. So basically all these things inside the square is a 1. Okay, it's a 1. So how many ones do we have? Well, we have the last one is 40, the initial one is 10, and we add also to add 1 to take into account the beginning and the end. So this will be 31. So this will be 1 divided by 4 pi square times 31. It's that clear? So I hope it is. Well, a nice exercise. We had to divide the initial function in modulus and phase and transform each one. Very, very, very important, the property on how to convolve a function with a delta. And then apply this trick to take out or get the final Fourier transform that we have over here. I hope the exercise is clear, and thanks for your attention. See you in another video. Bye-bye.